Okay, welcome everyone online. I hope you can hear me and everyone in the audience. It's with great pleasure that I would like to introduce, let me put my camera on first. I would like to introduce Tobias Röddiger. Tobias leads the Wearable Systems group at Karlsruhe Institute of Technology. And it works on a range of things, including biomedical, wearables AI, and the automation of their designs. In this group, where he's also a visitor, he has been instrumental in our work on Wearables because we use his OpenEarable device, and I hope he'll talk more in this talk about his development of such device and similar devices openly. So thank you, Tobias. I'll leave you to get the rest of the time.
Thank you very much. All right. Yeah. Hey, everyone. So I'm super excited to be here today to talk about building open wearables with AI capabilities. And before I dive in, let's maybe have a common definition of what a wearable actually is. Well, wearables are these intelligent embedded systems that are designed to be worn on the body, and they can help us improve our health and augment our abilities. But when we think about wearables, they're actually quite challenging to design because there is two aspects to this, which is that they're constrained in hardware. They have small memory, they have very low computing power, and also a limited energy budget. But at the same time, on the software side, we want them to be flexible with different edge AI applications. They should perform real-time sensor fusion. And also we want these wearables to provide different functionalities and different apps. But also, these wearables need to consider human factors, right? Like the unique physiology of a person or also their different behaviors. So if we think about this in terms of design challenges, at the top where we're talking about hardware and software, there is a lot of this traditional hardware and software co-design. We are trying to balance hardware against software and the computing power and the algorithms that you can achieve. But at the same time, wearables are also very unique because they need to consider things like ergonomics or different sensor placements across the body. And also they need to provide AI adaptation and usability to many, many different users. Now, this says a lot about the challenges that we're facing when we're building wearables, but it doesn't answer how we can actually build such intelligent embedded systems with novel AI capabilities. And this is what I want to answer today in my talk. How can we actually build such intelligent wearable systems? And to do so, let's just start with a warm example. And together, I want to build a novel AI wearable. And I want to start with talking briefly about the human brain. So I hope everyone that is listening has a brain. And inside that brain, there is many neurons. And all of these neurons, they are firing, they're active, and they create voltage spikes. So maybe some of you have also heard of spiking neural networks, which we use in computer science. So basically, when a neuron triggers some activity, then a voltage spike goes over this neuron, and this results in measurable electric potentials. The next concept I want to introduce is cognitive load. So as a simple task, maybe everyone try to add these two numbers, 27 plus 18. All right, 45. So let's go into the next one. 145 divided by 5 plus 38. Yeah, 67. All right. So you can notice it's taking longer and longer. And now this one is even harder. But I don't want to spend too much time on you calculating these things. So 570 would be the answer here. So what this clearly shows is that if we have tasks of increasing complexity, this also increases the cognitive load, so the processing that it takes to solve the different tasks. And this is a toy example with arithmetic operations, but you could do the same for things like object detection in whack-a-mole game or puzzles, text copying. These are all very well-established methods to vary the cognitive load of, for example, study participants. So what we wanted to find out is, can we use this or can we measure this cognitive load with a wearable form factor that we could use in everyday life? And the first thing that you need is actually a wearable that can sense something. So together with my colleague Michael Knirim at KIT, we developed this headset which uses the OpenBCI open source hardware to measure the electric potentials of the brain around the ears and also at the top of your skull. And inside this, there is a small microcontroller that then also does all the recording and transfer of data. So what we ended up doing is we recruited 39 participants and we gave them the tasks that I've shown you earlier, the 4 tasks. And we asked them to perform these tasks as increasing difficulties. And then here on the left, you can see ground truth recordings from a full scalp EEG. And on the right, you can see electrodes from a headphone-based EEG. And what we did is we implemented a very simple machine learning classifier that can predict the cognitive load at these different medical difficulties, where we could get 90% accuracy for 3 difficulty levels for the task that I introduced earlier. And these different colorizations, these are basically the Gini impurity gain of decision tree. So basically, when you're training a decision tree, at every leaf you make a decision if that feature is relevant. So this is basically the feature importance. And what you can already see here is that alpha activity is very important for the classifier, which is well known in the literature on cognitive load. Okay, so this was a very simple classifier, a random forest plot that can run offline on a device. And then we also took that into a field validation study where we actually gave out the headphones to participants and they had to put it on themselves. And then they were free to do any sort of knowledge test, which were things like programming, reading, and so on. And what we could show then is that we can still in the field, in these freely chosen tasks throughout multiple sessions and across different participants, we could get very high accuracy for predicting these different cognitive loads. Now, if we take this to the application level, what could you actually do with this? Well, for example, imagine you're working and you're working on a very complicated paper and formula and you're trying to get that solved. So as the headphones detect that you have high cognitive load, for example, we could disable the notifications on your system so that you don't get distracted. And then once the system would detect that you have more capacity to handle additional input, maybe only then we would send the notification to the user. Now, this is a very straightforward system of a wearable that does something intelligent and that uses AI to create a new application for the user and which augments their abilities. But I want to take this to another abstraction level, which is the process of developing such wearables. In our research, we believe that really if we're building wearable applications, you have to start somewhere at the human body. So this is everyone here has their own biology, but also it's shared and there is common phenomena across these bodies. So for example, your heart rate is a phenomenon of your body. Your brain activity is a phenomenon. So once you have this phenomenon, then you can use a sensor and this sensor can observe this phenomenon. And then with the help of edge AI, you can do inference, you put that into a device, and in the end, you create an application. And I think what is really important here to understand that this process starts very close to the human body, and it then goes down to the very technical level where it's about sensors and building electronics and so on. And then it goes back to the human where you integrate it into an application. Now, if we look at the ears are actually very versatile, and I'm sure many people in the audience know that the ear is so well perforated by different blood vessels. It's close to many muscles of the face and the skull, and also the ear is very unique in terms of that you can put devices there securely because it has different structures that can be used for anchoring something. So this opens a lot of opportunities for sensing many different things. And then also in a very recent study that is not published yet, we collected longitudinal data from 68 participants over 4 years. And the graph that I want to highlight here is on the right. So what you can see is over the past 4 years, the usage of earphones has actually been steadily increasing. So from an average session duration per session, of around 15 minutes, now it's up to almost 40 minutes. So really, it's steadily increasing, and people are using these earphones more and more in their daily lives. So this gives other reasons to maybe add more capabilities to these earphones. And if we look at what has been done in research, we can see that there is many phenomena that we can sense on the ears. And in these blue boxes, these are so-called fundamental phenomena. So these are things that we can fundamentally sense with a sensor around the ears. And then with the help of artificial intelligence, we can then derive higher level things. So for example, if you have a motion sensor, you can then use AI in order to predict things like your everyday activities or your energy expenditure and so on. And really, there is a lot of things that you can potentially do on the ears. But the question remains then, really, how can we effectively explore all of these many possibilities around the ears with hardware and software? So the next thing we want to do together is building a multi-purpose wearable AI platform. And if we rearrange the boxes that you've just seen here and add the sensors, the picture actually becomes quite clear. So on the left, you have the things that you can fundamentally sense with the sensing principle on the ears. And on the right, you have all the things that you could potentially derive with the help of AI. So what we need for now is, as a first step, we need all these sensors that we have in this list here to actually sense the fundamental phenomena. And if you were to say, hey, I want to build an earphone that has all these sensors, maybe your first prototype would look like something like this. So this is a prototype of an earphone where you can see, many different sensors. You can see the DSPs for audio. You can see all the controllers for the battery management, the microcontrollers, and so on. And then over many iterations, this brought us then to the OpenEarable. And so OpenEarable is the world's first entirely open source AI sensing platform, which means both in hardware and software, it's completely open source and anyone can build that on their own. If we look under the hood, you can see that there is a total of 9 sensors that we've integrated into a truly wireless form factor. So we have a 9-axis IMU. This can be used for basic body motion measurements, an accelerometer, gyroscope, and also magnetometer. We have 3 microphones, one into the ear canal, which uses air conduction, and one to the outside, also air conduction based. And then we also have a bone conduction microphone, which can be used to pick up these tiny vibrations that go over to your skull into the device. Then we also have integrated a PPG, so photoplethysmography sensor with 3 channels, red, green, and infrared, and also ambient light sensing, and also an optical temperature sensor. So maybe some of you know that the ear is actually a gold standard location for measuring core body temperature, and we can do that in an earable form factor. We also have, it can charge via USB-C, and then there is also the possibility to insert a micro SD card so you can store data locally. And of course, we also have a dynamic driver for getting some nice audio feeds and playing music and so on. Now, if we dig down deeper into the architecture, you can see that actually a lot of the components that we're using are from European technology providers. For example, we have been working a lot together with Bosch, with Melexis, and so on. And all of these components, some of them have been given to us even before they were released to the general public. And this really allowed us to create a cutting-edge device that can be worn on the ears and integrates a lot of different sensors. And also it's designed to be extensible. So the main PCB that you saw earlier that has all the processing on it has a flex connector, and there you could potentially add your own sensing to it. In terms of the computing architecture, the OpenEarable has also been designed for AI applications from the beginning. So we have 2 main processing units, which have both 2 processing cores itself. So the first one is the Nordic NF5340, and this has 2 cores, the application processor, which is used for handling all the sensor data and all the housekeeping of the system. And then there is also a dedicated network core, which does all the communication via Bluetooth. And then this connects to the analog devices 808-1860, which is a DSP, and that can be used for some very basic audio processing for low latency tasks on the audio, things like FFTs and so on, and it has a specialized instruction set architecture for that. But also it has the Tensilica Hi-Fi 3Z DSP core, and this is a dedicated core for audio-based AI. So it has things like multiple accumulate operation, and SIMD instructions and so on. And also there is a dedicated extensor neural network compiler that can be used to compile neural networks that can directly be accelerated by that chip to run offline on the micro or on the DSP. So I've said before, the whole device is open source, and this means not only the software, which many people probably know, open source software, but also the hardware. So every schematic, every layout, every 3D printing file, it's all out there on the internet, and we have an MIT license, so everyone can build one on their own. And I think this was quite successful. So already by now it has been well adopted by many, many different institutions, both from the university level, but also in the industry. We then also ran a series of validation studies where we compared the core temperature body measurements, heart rate, and blood oxygen saturation to medical gold standard devices. So I want to be very clear, these were not medical studies by any means, but what we could show is that the performance that we could achieve while the user was at rest and in lab conditions was within medical accuracy that you would expect for or would hope to have for such a device. And then we also ran different wearability studies where we had participants wear a series of different devices. And I would say probably the gold standard in terms of wearability are the AirPods. And we had people then wear AirPods for an hour and perform a series of activities and also wear the OpenEarable. And what you can see is that the OpenEarable is very, very close in terms of the wearability compared to the commercial form factors, which actually shows that this can be used to run studies that are very close to something that you would see in the real world. Now, we've also been using the OpenEarable in our lectures, and this is not just for the second generation of the device that I've just shown you, but also for the first generation of the device. And by now, our students have built over 120 apps that use earable sensing, and many of them are using AI. So this is usually implemented on the phone, not on the earable itself, but we have a library and you can see many, many different applications. For example, we had students build workout trackers where they measure their activities, things like sit-ups and so on, jumping jacks, sleep posture trackers. We had CPR support where you can measure chest compressions and also if you're performing chest compressions at the right depth and so on. We had some motion adaptive text sizing where it detects how your head is moving and then changes the text size and the motion so it's easier for you to read while you're walking. Also some dead reckoning applications, hands-free cooking apps. We had a Flappy Bird that can be controlled by your head. I don't know who needs that, but we have it. And many, many more. So really every year it's very exciting to see what our students are building. And they have all sorts of crazy ideas. We had headbanging counters. We had cookie clicker with headbangs. I don't know. So there's really, it's always a great source of creativity and people have great ideas. And at some point, we also created a video for one of the apps that one of the students built. So this was using the heart rate variability. So imagine you have someone that is working in a very high stress environment, and then you can measure the heart rate variability. And if you, after some time, this is now a lot of heat and so on in this environment. And at some point, some time passes. I got to cover the time until the video gets to where I can say the next thing. And then you can see the heart rate variability goes up and the person gets a warning that maybe they should take a break. Okay, so let's take this back to the process abstraction level. And I want to, build on the shoulders of giants, which is Bill Buxton, who has this very famous distinction between sketches and prototypes and what they are and what they are not. Well, if you think about earable computing and the way I have done earable computing before we had the OpenEarable, it was very much like prototyping. You define a very concrete thing that you test, and then you're trying to solve a specific thing with whatever you're building. But I think with something like the OpenEarable, exploring sensing on the ears becomes a lot more like sketching, where it invites you to try new things. You throw on the thing, you don't need to worry about how to set it up. You can just provoke new ideas, and these can be early and maybe they don't work yet, but it really allows you to explore these new ideas very, very quickly. But then if you look at the design space also at the beginning, with an OpenEarable, you can do many, many, many things. But if you were to build a company, then probably you would be iterating to a very specific feature that you want to flesh out. So you can see in the beginning, you have a very large design space, and then this design space gets smaller and smaller over time as you get towards implementation. And what happens at the same time is that throughout this process, the integration of hardware and software is steadily increasing, right? With every step towards the implementation, these two things move closer and closer together. So we have this line that steadily goes up, but the question is actually, how can we actually increase the speed of integrating hardware, software, and human beings, and how can we make that more efficiently? And that's why in the next step, together with you, I want to build a tool that automates edge AI. And for that, I want to work on a very basic task. So let's say we have the earables and we have a time series data set and different activities like standing, walking, running, dancing, and so on. And these are measured by the inertial measurement unit inside the earable. And we have already collected this data set, and we also know that we have a specific microcontroller that we want to use to solve this task. So in this case, we're going to use the NAF5340. And this gives us a hard limit on the compute and the memory that a machine learning model could have in order to predict all of these different activities. And then, we cannot use all of the memory and the compute. So that's why probably as a user, we'd be setting a specific memory and also latency limit in order to also still be able to do all the other things that our earphones might have to do. And then the question is, how can we have an AI model that can predict within these constraints all of these activities that I've shown on this slide here? And the question is, can we do this automatically? Because we have all the information that we need, right? We have the time series data set, we have the dedicated microcontroller, we have the budget for latency and memory. And this is why we then designed Micronas, which is a hardware-aware differentiable neural architecture search principle. And it basically introduces three main things. The first one is an inference latency characterization method that we can use to characterize inference of different architectures on a microcontroller without running it on the microcontroller. Then this paper introduces a time series specific superarchitecture for solving sensor-based tasks that are evolving around HAR, and then also a hardware-aware training procedure to make sure we actually fit within these constraints. And the result of that is then a machine learning model that actually can predict these different activities within the limits that we give it. So the first concept I want to introduce is differentiable neural architecture search, and we didn't invent this. This is a well-known established concept for some years now. But the basic thing that you need to understand is, let's say we have an input and we have two different potential operations that we would want to do, maybe a max pooling or a convolution operation. And then with the help of differentiable neural architecture search, we introduce these architectural weights. So these are basically in our architecture, and we can use them to decide which path in our architecture we are taking. So basically you softmax these, and then in the end, throughout the training, you are optimizing these architectural weights, and in the end, you then can one-hot encode whichever architectural path is the best, and then you get to the final architecture. And of course, you need the add operation in the end to make sure that the whole architecture is still differentiable. Okay, so this gives us an opportunity or a possibility to take different paths in a super architecture, but then also we want to be able to configure convolutions. And for that, I want to introduce dynamic convolutions. So dynamic convolutions use masking principle. So basically, you have a convolution, and with the help of these masks, you can mask out the number of filters. So let's say you have 10 filters, and then these masks, you have, or let's take 12 because it's divisible by 3, but you have 12, 8, and 4 filters, and then you can tune these architectural weights in order to decide how many filters do I actually want to use inside that one specific convolution. And then also we can use these filters, these masks, in order to decide how long is it going to take to run a filter of that size on a specific microcontroller. So basically, we can pre-compute how long is the inference time going to be of any of these number of filters on a microcontroller, which we can then use later on in the hardware training process. Okay, the next building block that we need then is the super architecture that we will actually use in order to train something and find something within or for the specific use case that we're building. And for that, we're basically introducing an architecture that is very much inspired by TinyHAR. So maybe some of you are aware of TinyHAR, which uses the combination of time-reduced cells, where you're trying to reduce the complexity on the time axis. And then in the next step of the model, you have the sensor fusion cells, which basically perform cross-channel interaction across different channels. So in the time-reduced cell, so the number of time-reduced cells totally depends on your input length. So with log2, basically, we're reducing that until we shrink the time series to a desirable length. And then here you can see now a breakdown of the time-reduced cell. So in this case, there is 3 different options on how we perform the convolution on the temporal axis. So filter size 3x1, 5x1, and 7x1. And basically, through neural architecture search, we can then decide which filter size are we going to use. And within these convolutions, we also have the masking, where we can then also decide how many filters do we have for this filter size. Okay, and then in the next step, there's the sensor fusion cell. So here, again, in the first bit, we're performing cross-channel interaction, so interaction between the different sensor channels. And then, again, it was found also in TinyHAR that after performing the cross-channel interaction, it's beneficial to still perform temporal convolutions. So after the cross-channel interaction, we are also performing temporal convolutions. And then maybe at some point it doesn't make sense to keep, mixing sensor channels. So there is also the possibility for the super architecture to learn a skip connection in that scenario. Okay, so now we almost have all the building blocks that we need in order to learn hardware aware. And the last thing that we have to add to the formula is the hardware aware training procedure. And for that, we have basically a combined loss here, where we have the very normal cross entropy loss. So that is just optimizing the performance of the network. But then we also have a latency and a memory loss. So you can see them here, and basically this let alpha MCUT, basically you put in the architectural weights, and then we through pre-characterization of the microcontroller, we can then, without actually running the architecture, we can predict, or we can compute, not predict, through a lookup table approach, we can compute how long is the inference going to take on that microcontroller. And for the memory, it's a lot easier. There you can just take the parameters in the architecture that you get from the architectural weights, and then you will know how much memory is your architecture going to use. Okay, and with this, we can then optimize the model within the constraints. And now if you look at the results here, so we use different benchmark data sets and that are well established, and also a series of different microcontrollers. And what you can see here is 2 things. So first of all, you can very precisely tune the latency. So as you increase the latency budget, you can make use of that and also get higher accuracy. And this works across different data sets and also across different microcontrollers with different computing power and different memory. But also you can precisely tune, for example, for memory. So as you give the model more and the architecture search more memory, you can then also get higher accuracy scores and so on. And then what is also really cool, I mean, I introduced TinyHAR as the sort of inspiration and the gold standard for these tasks. I mean, by now there is also TinyHAR, but with the help of MicroNAS, we could then find architecture that achieve very close to state-of-the-art performance on these hard tasks. But the model is half the size, and we can find that automatically. So if you think about, any new wearable use case, now you just take the data, you take the characterization, you throw that into MicroNAS, and then it will automatically find a suitable architecture for whatever you're trying to do. Now, of course, by now there is some other models like transformers and so on. So maybe you could also design super architectures for that, where you then also can perform neural architecture search to automate the whole process. Okay, so now I've shown you a lot of things that we have built in the past, and now I will briefly talk about some other past things. But then I also want to touch upon what can we actually build next in wearable computing, and where I think the journey, at least for me and the other people in our lab, will be going. In terms of wearables, I think there is a massive potential still to do a lot of things. I mean, we're still very far away from having wearables that make a big impact on your health and so on. And I really want to push on that frontier. So here on the left, I want to show you a short example. So this was in Munich, and we had built a device that can detect small contractions of the muscle. So maybe some of you that were here for my last talk remember the ear rumble device, where you can measure the muscle activity. And actually, there's some people that have a so-called myoclonus. So that's an involuntary contraction of that muscle, where it's a bit like tinnitus, but based on the muscle. So you know the source, but there is no objective diagnostic method. So here, this was pre-surgery. We put into the device into the ear, and then after the surgery, we could show that this muscle twitching was gone based on the device that we built. And yeah, this is me then showing the device to all the people that work there who are quite fascinated by it. But then I think wearables is not only about humans. You know, we can also build wearables for robots. So, for example, while I was at MIT, we worked on. I collaborated with them and supported the efforts on the Astro Ant, which is a wearable for space, which can actually has magnetic wheels, and it has a temperature sensor on the bottom. And because you have a lot of or temperature differences in outer space, sometimes there is sun, other times there is no sun at all, and it gets really, really cold. And you cannot have temperature sensors anywhere. So with the help of Astro Ant, you could crawl around the outside of a spacecraft, and then you have your small wearable, robot wearable that can sense different things in different locations. Now, just because we've been freezing, I've been freezing in the past few days because it's really cold here. I have another short video that I want to show you of some past work that we did. So actually, oh, I hope this audio shares over Zoom. Yeah.
It's had the demos, so just wait for us.
All right. Yeah, so I will just play it now. And
in shared offices, it's hard to meet everyone's thermal comfort needs. While one person feels fine in a t-shirt, another is shivering at 17.5 degrees Celsius. To address this, we present Heatables, an in-ear device that delivers warmth into the auditory canal. This region is richly vascularized and therefore a sensitive site for thermal stimulation. With Heatables, perceived ambient temperature can be increased by about 1.5 degrees Celsius through infrared LED-induced warmth. This effect was confirmed in our study with 24 participants. What works at the desk may also be applied when cycling against cold winds, or simply for additional comfort at home on the couch.
All right. Yeah, so this was some really cool work by Valeria, and you can see, I think for wearables, a lot of the times we're still thinking about diagnostics, what are some things that we can measure and detect. But I think there is also potential for wearables to perform, I don't want to say treatment, but some sort of input into the human body that then triggers something. Also, Jeune, one of our other PhD students, she's been working a lot on haptic feedback for relaxation and so on. So I think there is also a lot of potential in that regard.
In shared offices.
All right. Yeah. Then in terms of phenomena that we can sense, in recently, I collaborated in a paper together with Tsinghua University, and there the analyses that you could see for the ears we've done that for fingers. So what are all the phenomena that you can sense on the fingers? And I think we can greatly, leverage this information to also produce other next generation wearable devices, which, for example, is why currently we're also working on an open ring, which will be open source and will have a lot of sensing that also goes beyond of what you can find in commercial offerings for wearable rings. And this then is already leading to something that I want to call the Open Wearable OS. So we can reuse all the effort that we've done for the OpenEarable, and we can bring that to other wearable platforms. And we have first prototypes now also for an embedded runtime, where you can then have edge apps that can run on these platforms. So basically, the vision here is really that you can have tiny programs that you can send to your wearable, and then you can run them directly on device where you can do inference and so on. And then also all these things should connect to the Open Wearable app. So the OpenEarable already works with it. We also have support for the Polar watches, for eSense, cosinus, the Polar chest straps, and so on. And the vision here really is that the Open Wearable app, even though it says Open Wearable, should support any wearable out there that is willing to share its data. And it's all open source. So if you ever build a wearable and you think that is worth sharing with others and you want to integrate that, we are very happy to receive any contributions. And then for the machine learning part, for some time now, we've been also working on HML. So this is an entirely web-based TinyML web platform where you can upload your data, and it has all the labeling and so on features, and also integration for different neural network architectures and so on that you can then train directly in the cloud. And the vision here is really that at some point we'll be able to have the full process. You take your open wearable, you collect some data, you throw that into HML, and in the end you get some result out of this. And this is why we're also starting a community around this. So next year, hopefully, we'll have the 3rd edition of the Open Wearable Workshop. There's also already a lot of great universities collaborating in this environment where we are building open hardware, open software that can be used for creating new things. Okay, but to wrap up my talk, I really want to provide a more abstract vision of what I think is going to be the future for how we design such embedded systems. If you look at the very first example that I gave, I would say this was manual co-design, right? You have a developer that specifies a certain thing that they want to do. So for example, they want to detect cognitive load. And then they design a specific hardware that is made for purpose. And then you implement some specific machine learning classifier. And then with the human in the loop, you can create a system. But I think in the future, we will steer towards something that is more something like autonomous co-design, right? Where the developer commissions something to an AI and tells it, hey, I need a certain system that does this. And I mean, for software, we are already seeing that there's a lot of things going on with generative AI for generating code. But also, we are now working on how we can translate these concepts to generate new hardware. And also, there's a lot of great work on understanding how we can actually generate human data, right? So we don't even need to get participants into the lab anymore. We can just do that with the help of AI. And if you look at the recent papers that try to solve HA, you could argue that HA is solved, but anyways, you can then generate new data. And if we, look at the skill and the time that it takes, really manual co-design is something that was reserved for experts, right? You have someone that is highly trained and it would take them months to build something. With something like the OpenEarable and Micronas and HML, now it's possible for beginners. Our students are building Earable apps in our lecture, and this is a very short period. And they are able to design something within days in our lectures. But I think with autonomous co-design, the vision is really that anyone within hours can create something. And I want to tell a short story. So Jake and Matthias told me that during the Cambridge Science Festival, there was a small child playing around with the earball, and they were, hitting their face to see how the microphone reacts, and they basically were evaluating different gestures, if you want to say. So imagine if that child had the right tools to just tell an AI system, hey, I want this thing to be able to detect this, and then the AI takes over and commissions something for them that is ready and can be used without any knowledge of how it works internally. So I think this will be very big for embedded systems, and that's why I also believe that autonomous co-design will not only be relevant for wearable computing, but it will be relevant for many industries. And I'm really hoping that we'll be able to solve things like generative hardware design, which turns out to be quite challenging. Yeah. All right. So that's my talk. Thank you very much.
Okay, I'll come here to hear the microphone. If people have questions, please put them in the chat and I'll read them out on the microphone. And audience, if you have questions, please ask them now.
Thank you.
And this pre-characterization works for as you mentioned, that you don't need to run anything on
Right. Yeah. So basically, if you take one convolution and it has a certain size that it's going to have, right? You basically put an arbitrary input into that and then do the inference once. And then while it's doing that, you record how much, how long is it going to take for that to happen? Of course, microcontrollers are not that easy. If you have a certain value, maybe that's going to take a little bit longer. So that's why there's still a bit of noise. But basically, you compute that once. So you need to know the super architecture in advance. But once you've done that characterization, then you just have a lookup table, and you can then based on once you've done the one hot encoding, you can say, okay, this is the filter size or the number of filters I have, and then you can just retrieve that number. That needs to be run on the physical hardware. Yeah. But you can also proxy it with the number of flops and so on. But we tested it, and it's actually quite very inaccurate. Yeah. Sure.
More general process. So you have the headphones and the imaging devices to compare with using the classifier.
Yeah.
Performance comparison. Do you really compare the quality of the signals from the EEG device and the near?
Yeah. So if you go into the paper, you will be able to see that we have basically the same setup or the same data evaluation for the full scalp EEG and also the ear-based EEG. And there, of course, the full scalp EEG works better. And we also did some additional experiments. I mean, if I jump back here, you can see alpha activity is actually the most important. So this is in the prefrontal cortex, where a lot of alpha activity is going on. So actually the electrodes on top of the head are very valuable to predict something. But in the paper, we then also looked at if we just use the electrons around the ear and so on, how is that going to affect performance? And as you would expect, it then decreases further. And also it's quite interesting in terms of the tasks, the math task seems to work a little bit better. And I think that's just because it's more consistently challenging for people than the others.
I'll read one question online in the meanwhile. I'm not sure I understand fully the question, but first of all, they're thanking you for the presentation, and then they're asking, are privacy ethics protocols in place with respect to personally identifiable information from the on-site offered by your product, or is it something delegated to whoever uses the device software on the study's experimental final products?
Right. I mean, of course, we have ethics for everything that we're doing, and we get approval from our institutional review boards.
Studies.
Right, that's for our studies. And then for the Wearable, of course, this is very much up to the person that is using that wearable to do something that is not harmful. In some respects, the things that you can do, or the harm that you can do with it, are limited. When you get the OpenEarable, for example, you get raw data out of it. There is no continuous recording. It's explicit and so on. It's not a device that is intended to record 24/7. But of course, we have to trust the person who ever uses it has good intentions.
Perhaps just turning on this question, there are some aspects related to safety certification and things.
Yeah.
Can you share any more about that?
Yeah. So as the Wearable is within all the guidelines that we have in the European Union. Yeah, it's not a CE certified device because it's a one sample prototype device that is custom built for every person that orders it.
Thank you. Adam, Magic.
Just on this project again, how do you get ground truth data?
Yeah.
Because you have sort of one electrode in each position, right? And I assume they're not connected to both the headphones and the ground truth device.
Right. Yes. So these were two separate sessions. So yeah, exactly. Yeah, you have to assume that. Yeah.
Or the education, be ready to do the project, ready to work, it's used like that.
Yeah. So the Michael Küttner, who is the guy who's doing all the firmware stuff on the OpenEarable, he's been using that for some projects, or is starting to use that. But it takes some time. We hope that at some point we'll have some tutorials online on how to use it, because this is not just Arduino. It's really deep down technical stuff.
Do you think it's required to perform on-device training, and do you think it would fit in the form factor? You mentioned that also about continuous 24/7 recording and the streaming. Do you think that you reach a stage where you do that easily on
device? I think training a whole architecture on a wearable in the category where it's an earphone or so is quite challenging. So you can definitely you will not be able to, in a reasonable time and energy budget, train something. Maybe you, but then these devices charge, for example, or they're in a charging case, and then you can use this to do some, maybe freezing, unfreezing type of things where you freeze the model and you have a last layer that you train. So this is very realistic and it's already done. Yeah, that would be a cool idea. Yeah, so yeah, I would love that.
There's a question, perhaps related to something you already answered. In the initial slides, when you talked about field experiment for the cognitive, scroll down, for the cognitive load task evaluation headphones, how was the ground truth generated?
Yeah.
How did you deal with the subjectivity of perceived task difficulty? Some tasks are easy and some tasks are hard for others.
Yeah. So this was an experience sampling style method. So basically you continuously probe the user and they will have to self-report, and then we're using NASA TLX for it. Yeah. But the tasks were the same across participants. Yeah. Okay. So that was not calibrated, but we could see that across participants there was statistically significant difference in the perceived complexity of the tasks.
Okay. Thank you. I have one final question.
Sure.
Will you raise your hand? Yeah. Oh, sorry, go on. Not the final question.
So obviously the Wearable 2 is a big step from
right.
this one. You got any of the things that you can get into that you want to do in the future with the Wearable?
Yeah. It's nothing that is concrete at the moment, but one thing that is missing is biopotentials in the OpenEarable, but that's to be determined. At the moment, we're still very much on the OpenEarable 2.
Okay, and my final question is, do you have a video of a demo of was that a flapping bird that the students?
Yeah, I don't have a video, unfortunately. Yeah.
Fair enough. Thank you very much.
Thank you.
Okay, online audience, this is the last seminar of the term. So we'll see you next term. Bye-bye.